Electronic transitions, that's going to be the topic of this lesson, and it turns out that atoms can either absorb or emit photons of light, the subject of the last lesson here, and it turns out it's related to the electrons in the atom jumping from different energy levels. When they jump up an energy level, they have to absorb a photon of light. When they drop down an energy level, they emit photons of light, and so we're going to focus mathematically on these different energy levels, and then in the next lesson we'll actually go through and get a little better description of what's really going on and what are these energy levels we're talking about. Now, this lesson's part of my new high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year, so if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I post a new lesson. All right, we're going to start this lesson off taking a look at what's called the Bohr model of an atom. And Bohr had an interesting model of the atom. It's not completely correct, but he got one non-intuitive thing right that nobody else initially saw, and that's why we give him a lot of credit. So now he thought that the nucleus was at the center of an atom, and he was right. That's where the protons and neutrons are and stuff like this. And he thought the electrons were around that nucleus, and he was still right. Now, here's where he kind of went off the rails a little bit. He thought that the electrons were going around the nucleus in circular orbits. And some orbits were closer and some orbits were further away, but these orbits were at exact radii. And it turns out we can relate the energy of an electron in an orbit that's attracted to that nucleus based on how far from the nucleus it is. And he knew from data the exact energy of electrons in a hydrogen atom, and so he figured out and worked out the math and said, well, that just means they have to be at a certain distance in a circular orbit from that nucleus. And it turned out the math worked out fantastic for the data corresponding to hydrogen, and it turns out the math corresponded really well for anything having one electron. And for neutral atoms, that means only hydrogen. But once he got to any multi-electron system, his model broke down and failed miserably. But we do give him a lot of credit because he said that electrons can only have certain energies which match the data, and he said that they only can have certain orbits. Well, it turns out that electrons don't actually have these circular orbits. They live in what we'll find in the next lesson are called three-dimensional orbitals. But the fact that only these certain orbits that correspond to only certain energies, that's what we call a quantized model, where electrons can only have a certain quantity of energy. And that's what we give him a lot of credit for, because that is not intuitive. If you think about the implications of what something that is quantized might be on the macro scale, you might think like, let's say I have a quantized car. And my car, only certain quantities of speed are possible. I pop it into first gear and it only goes 10 miles per hour. And I pop it into second gear and it only goes 20 miles per hour. I pop it into third gear and at third gear it only travels at 30 miles per hour. And at fourth gear, only at 40 miles per hour. And those are the only possible quantities for speed that my quantum car can go. And the interesting thing is, once I go from first gear to second gear, from 10 miles per hour to 20 miles per hour, it doesn't actually speed up from 10 to 20. It instantaneously changes from going 10 to going 20. It never actually goes from like 10, 11, 12, 13, 14, 15, up to 20. It actually just instantaneously changes its velocity from 10 miles per hour to 20 miles per hour. That's my quantum car. Nothing in our macro world works like this at all. And so this was not intuitive, and that's why we give Bohr so much credit. Even though his model's not 100% correct, he did get the idea that these electrons were quantized, and people just thought he was out of his mind because it's just a weird idea, but he's totally right. And again, electrons aren't actually going around this nucleus in circular orbits like his model is. We still find his model helpful from a conceptual standpoint. We're going to use it here in this section. But it turns out we still give him a lot of credit again because electrons are indeed, or at least the energy of electrons are indeed quantized. That is kind of the basis of quantum theory, which sounds like a really heady topic, and it is, and it's really math intensive, but at the basis of it, quantum theory really just says that electrons and other things like electrons can only have certain quantities of energy. Okay, so in this Bohr model of the atom, it turns out there were orbits going around the nucleus that got farther and farther away. And as they got farther and farther and farther away, they ended up with more and more and more energy. So the lowest energy orbit was the one closest to the nucleus, but you get these orbits further and further away. Well, it turns out in Bohr's model here, there's an infinite number of these orbits that just keep getting further and further away. Okay, so And it turns out each of these orbits is going to get a number associated with it, and we'll find out later on in this chapter that's called the principal quantum number. So we use n to represent that number, and this is the n equals 1 orbit, the n equals 2 orbit, the n equals 3 orbit, then there'd be 4, 5, 6, 7, 8, all the way up to infinity. And it turns out for hydrogen, there is a very simple relationship to describe the energy of an electron in that orbit, and it is this lovely relationship right here. So En, where n could be 1, 2, 3, just integer values, is equal to negative 2.18 times 10 to the negative 18 joules divided by n squared. It's actually, remarkably, just a very simple formula for calculating the energy of an electron in any one of these orbits. Okay, so if we want to do this for like n equals 1, so we'll call this E1, and it would just be negative 2.18 times 10 to the negative 18 joules divided by 1 squared. Well, 1 squared is still 1, and anything divided by 1 is itself, and so this just comes out to negative 2.18 times 10 to the negative 18 joules. If we want to do this for E2, well, in this case, it'd be negative 2.18 times 10 to the negative 18 joules divided by 2 squared, i.e. divided by 4. Now let's use our calculator and figure out what that's equal to. Actually, I've got it on your study guide there, so I'm just going to read it off your study guide. That's going to equal negative 5.45 times 10 to the negative 19 joules. All right, we'll do the same thing for E3 here. In this case, it'd just be negative 2.18 times 10 to the negative 18 joules divided by 3 squared divided by 9. And if we plug that in, or just read it off our study guide here, that's going to give us negative 2.42 times 10 to the negative 19 joules. Cool, so you can see again there's an infinite number of these orbits. We've only got the first 3 on the picture here, but there'd be a 4th and a 5th and a 6th and a 7th and an 8th, and so on and so forth. If you notice, if you go all the way to the infinitieth level, well, if you divide this by infinity squared, which is really big, infinity squared is still infinity, anything divided by infinity is 0. And that is, again, you go from lower energy to higher energy as you work your way out. And so your outermost orbit, the infinitieth orbit, has an energy of 0, and that's the highest energy. And that's where things are weird. So your highest energy, infinitely far away from this nucleus, has an energy of 0. And as you get closer and closer, the energy goes down until you reach right here, where it has an energy of negative 2.18 times 10 to the negative 18 joules. So notice if your highest energy is 0, then as you lower your energy getting closer to this nucleus, it gets more and more and more negative. And the most negative it's ever going to be is negative 2.18 times 10 to the negative 18 joules. All right, so it turns out an electron can have these different energies. And what happens is that an electron has the ability to jump from one orbit to another according to Bohr's model. And when it does, it either absorbs or emits a photon. Now, it turns out if it is going further away, then it's going to go from low energy to higher energy, and it's going to need to absorb a photon to make that possible. But if an electron actually is going from a higher energy orbit, one further away, to a lower energy orbit, then actually instead it's going to emit a photon of light instead. And so it turns out atoms inherently have this ability to either absorb or emit photons of light. And it turns out even more than that, atoms only absorb or emit certain photons of light, certain colors, if you will. And I say colors, but it's not always necessarily in the visible region of the spectrum. And it turns out it's different for different atoms. Different atoms actually absorb and emit different photons of light. And there's only certain possibilities based on the energies that are characteristic of that atom. What's interesting, if you look at white light, and if you don't know this, white light is actually all of the lovely visible wavelengths. If you look at white light and you shine it through a prism, you can see that it has all those colors in it. Well, if you take white light that has come from the sun and you shine it through a prism, you actually find out, you spread out all those colors, that there are going to be certain colors that are missing. You'll see certain black lines. And it turns out from which colors are missing, we find out that if we take white light and shine it through hydrogen and helium gas on Earth, and then expand it through a prism, we see the exact same colors missing. This is actually how we know that the sun is made up of mostly hydrogen, 75% hydrogen, 25% helium, and trace amounts of other elements, but mostly just hydrogen and helium. And we figure that out based on the light that's coming off that sun. And so the idea is that the the colors of light that are absorbed or emitted by an atom are a fingerprint for that atom. And that's how we can tell, even distant stars, we can actually figure out what those stars are made up of based on what is either, what black lines are missing from the light coming off of those stars. Cool. If we look at the black lines that are missing, we call that the absorption spectrum. It's the colors that have been absorbed out of the white light. You can also do this a different way. You can actually zap, a collection of atoms with electricity, which is going to cause these electrons to jump out to these higher levels. And then they're going to fall back down and emit photons of light. And that would be what we call its emission spectrum. And so instead of seeing like, the entire, visible spectrum spread out through a prism and just seeing black lines missing, in this one you see all black and then you just see individual little colors that were emitted, and that's the emission spectrum. But the key here is that the absorption spectrum or the emission spectrum really is a fingerprint of an atom, and we can use it to identify things. And we can also figure out the energy of those photons by looking at this lovely simple diagram here. So let's say we wanted to look at an electron jumping from shell 1, or n equals 1, from orbit 1 to orbit 3. So from E1 to E3, my first question is, well, what is the difference in energy between those two orbits? Well, I could just take and subtract the difference here, and that's exactly what I'm going to do. So in this case, we're going to calculate delta E, just based on the fact that we already calculated these energies. Had we not calculated them, I could go, through that process and calculate them. And so in this case, if we're going to go from 1 to 3, then I want to calculate from here the final minus the initial here. And in this case, so I'll take negative 2.42 times 10 to the negative 19 minus a negative 2.18 times 10 to the negative 18. And we're going to get 1.94 times 10 to the negative 18. Cool. And it turns out that difference in energy from whatever, and again, we could go from 1 to 2, 1 to 3, 1 to 4, we can go from 2 to 3, 2 to 4, 2 to 5, any different possible combination we want. But we have a very simple way, of calculating the energy from where it starts and where it ends up, and then calculating the difference between the two. In fact, we can actually make this even easier with a lovely equation. We can say that the difference in energy equals negative 2.18 times 10 to the negative 18 joules times 1 over n final squared minus 1 over n initial squared, and get a simple equation out of this. So notice that both these terms were derived from that lovely constant right there. And I'm just going to factor that constant out and then factor out the 1 over n squared for each of those two terms to get that difference. And so if you plug this in right here and just do 1 over 3 squared, 1 over 9, minus 1 over 1 squared, you're going to get this same answer. And so that, we could do it this way just from, calculating them each separately as energies and taking the difference, or we could have used this formula, which is on your study guide as well. So either one of those works. Just want to show you the utility of that lovely little formula. That way you don't have to actually go through and actually calculate the separate energies of electrons in those different orbits. Cool, but it turns out that difference in energy just so happens to also equal the energy of the photon that is either absorbed or emitted. Now, in going from orbit 1 to orbit 3, we're going from low energy to high energy, and again, that's going to mean going to require us to absorb a photon. So, however, had it been going from 3 to 1, that would be emitting a photon. Now, one thing to note when you do this, you just want to make sure that your difference in energy always comes out positive. Because technically, if you go from 3 to 1, this delta E is going to come out negative. But the negative really just means that you're emitting a photon rather than absorbing a photon. It's a negative energy change. You're giving off that energy. But when you actually go to plug it into the energy of your photon, you always just want to take the absolute value of that number. So whether it comes out positive or negative, just use the absolute value as the energy of the photon that's either absorbed or emitted. All right, and again, if you recall, if we know the energy of a photon, we learned in the last lesson that you could also calculate either the wavelength or the frequency as well. And in this case, we're going to calculate out that wavelength. So we learned that E equals hc over lambda. This is one expression relating the energy of a photon to the wavelength of that photon. And if we rearrange this a little bit, we can say lambda equals hc over E, and we can just plug this in and plug and chug and get the wavelength of this photon. And so in this case, we'll get 6.626 times 10 to the negative 34 joule seconds. There's again Planck's constant. Don't have to memorize it. Speed of light 3.0 times 10 to the 8th meters per second. Once again, a constant you don't have to memorize. And then we'll just take the energy of our photon. We calculated the difference in energy between the first and third orbits and plug that in right here. 1.94 times 10 to the negative 18 joules. And we'll calculate out that wavelength and let our calculator do the work for us. So once again, 6.626 times 10 to the negative 34 times 3 times 10 to the 8th divided by 1.94 times 10 to the negative 18. Sure I've got this all correctly? No, I don't. I jacked one part of this. Let's try this again. 6.626 times 10 to the negative 34 times 3 times 10 to the 8th. There we go. And then divided by 1.94 times 10 to the negative 18. And gets us 1.02 times 10 to the negative 7. Cool, and that's going to come out in meters. If you look, our joules right here are going to cancel, our seconds right here are going to cancel, and it's going to come out in meters. Now, commonly for wavelengths, especially for stuff in either the visible, ultraviolet, or infrared ranges, we often report these in nanometers, so it wouldn't be super surprising for this to show up on a multiple choice question with units of nanometers. But from the calculation itself, it's always going to come out in meters if we use the constants provided that are in SI units. And so you'd have to convert this, and that would come out to 102 nanometers if we went through and converted that. Cool. There's also another equation that allows you to calculate your wavelength directly. And we get what's called the Rydberg equation. It's 1 over your wavelength equals, and this is one constant I definitely don't know off the top of my head. I'm going to look at it. 1.096776 times 10 to the 7th meters to the minus 1, I believe. Yep. 1 over n1 squared minus 1 over n2 squared. Now this is what's known as the Rydberg constant. So we could derive the Rydberg constant if we needed to, but we're not going to do that. But if we wanted to go straight to wavelength, this equation is often provided as a way of calculating that wavelength. So, and this is kind of where Bohr got a lot of his math from, was a simple equation like this, at looking at the energy of the photons that could be absorbed or emitted by an atom and coming up with a relationship for wavelength. So N1 and N2 here don't actually mean necessarily E1 and E2 coming from those necessarily, but it really means like N initial and N final. But Rydberg's equation used 1 and 2, but it's really kind of an initial and a final kind of thing. Cool, but when you plug this in, you then take the inverse of this. Since this equals 1 over lambda, then the inverse of all this, 1 over all this, equals the actual wavelength, and we would have calculated out this same number directly using something like this. So sometimes they might want to have you calculate the energy of a photon, so which uses an expression like this, or you could just calculate the energy levels of the two and take the difference between the two. So, and then from there, you could calculate out the wavelength as we did. But if the question was asking you to go straight to wavelength, it might just be simpler and more direct to get it through Rydberg expression. All right, so I want to take a quick look at what we call the emission spectra for just a second. And again, if we zap atoms with electricity, the electrons get what we say excited. They jump from lower orbits, closer orbits to the nucleus, out to higher energy orbits. And then when they fall back down, they're like, oh, I like being back closer to my nucleus. I'm attracted to him. When they fall back down to these lower energy orbits, the ones closer to the nucleus, they're going to emit photons. We just look at which colors are emitted and stuff like this. And well, it turns out different series we call are possible. So let's say that an electron jumped up to orbit number 2. Well, instead of looking at this in kind of like looking at the radii and stuff like this, we can look at just a diagram that shows the increasing energies of the different orbits. So E1 here corresponds to the energy of an electron in n equals 1. E2 corresponds to the energy of an electron in n equals 2 orbit, so on and so forth. And what you find is that as they go higher, they actually get closer and closer and closer together in this respect. So, however, if an electron had jumped up to number 2, let's say, orbit number 2, then it would have the chance to fall back down to orbit number 1. So, but had it jumped up to orbit number 3, then it would have an option. From orbit 3, it could drop down to orbit 2 or drop down to orbit 1. Well, for a minute, I only want to consider dropping down to orbit number 1. And no matter where this electron ended up jumping up to, as long as it drops down to orbit number 1, this is going to give us what we call the Lyman series. So as long as you dropped, your photon drops down to orbit number 1, any one of these colors of light would be called a part of what we call the Lyman series. Okay, and it turns out most of these are in the ultraviolet range, so, and not something we can see with our eyes. Now, if we take this up and do another series, we could talk about electrons that jumped up higher than 2, that drop down only to orbit number 2. And again, I stopped at 5 here, but there's 6, 7, 8, all the way to infinity again. And as long as you end up at orbit 2, notice these energies are going to be lower than these energies of the Lyman series right here. And if these Lyman series ones are in the ultraviolet region, it turns out that many of the lines in this next series are going to be in the visible spectrum. And as a result, the Balmer often gets a lot of lip service. So because these are the actual lines in this series that we can see with our eyes. And so it's worth making a note here that some of these different series, I got the Lyman, the Balmer, turns out dropping down to 3 would be the bracket. The Paschen, and then dropping down to 4 would be the bracket. Don't care about any of those. I don't even care about the Lyman, truth be told. But the Balmer, where we end up at orbit number 2, from anything higher to orbit number 2, those correspond to visible light, and that's just worth making a mental note. If we're going to ask you anything about any emission spectra or emission series, it's going to be the Balmer series, specifically because it corresponds to visible light. If you look at the Paschen and bracket series, it's dropping down to 3 and 4, those actually are lower energy than visible light. They're usually in like the infrared range and things of that sort. The only one that tends to have any lines in the visible spectrum is that Balmer series. Cool. If you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to help promote the channel. And if you're looking for the study guide that goes with this lesson, or if you are looking for practice quizzes and chapter tests and things of a sort, check out my premium high school chemistry course on chadsprep.com.